Cool. All the tech works amazingly. So we're fortunate to have the working group chair of Anari. It's a new renderer that's actually going to change the world. Not enough people know about it, so you're lucky to be here. And Jeff is going to give us the inside track. So Jeff, over to you.
Thanks, everybody, for coming. My name's Jeff Amstutz. I'm a software engineer at NVIDIA. I work on a lot of scientific visualization, but I also have the privilege to chair the Anari working group, and just want to see it succeed in as many domains as possible, so it's not at all limited to sci-viz. So hopefully this overview talk will motivate that. I know that Anari is something that's very new, and so I don't want to assume anybody in this room is an expert on it by any means, so this will be a little bit high level, but I'd love to talk about as many technical details as you possibly could think of. Just come find me if we run out of time in this BOF. But I'm going to start with just highlighting what is the problem that Anari is seeking to solve. And what it is you have application developers who want to use 3D rendering in their app, and they want to use potentially state-of-the-art 3D rendering engines that are out in the wild. And so let's say you're a ParaView developer and you want to use Osprey, Radeon ProRender, VizRTX, and Cycles. What you have to do is a software integration to all of those, which is not an intractable problem. It's not too bad. The problem is that everyone has to then start doing this over and over again. And I don't know about you, but that's just 3 applications on the left and 4 rendering engines on the right, and that already looks like a mess. And there's just so many more out in the wild. And so what Anari does is standardizes the API for how do you talk to an engine. It's not implement an engine, but how do you talk to one. So that way applications, when using these, can use a single API that makes them all look similar, at least how the API functions are spelled. And then engine developers can have all applications have similar spellings for how things come in to that engine. And so I was presenting this, our version of this talk at HPG, and there was also a talk on Vulkan at HPG, and during that Q&A, it came up that Vulkan's not for the faint of heart, so Anari is for the faint of heart. So yes, Anari is of course part of Khronos. If you're here, you should probably be no stranger to Khronos, but Khronos has been a fantastic vehicle to develop a specification and to do so in a protected way that also doesn't limit us technically. And so I'll speak on this more at the end for how you could come participate, but we get to participate with a lot of great standards that already exist in the ecosystem for many years. So a brief flyover of the timeline of how Anari came to be. After being in an exploratory group, we started an official working group in 2020, and we worked for about 1.5 years on getting our initial provisional specification out. So the bottom row is about highlighting, those are going to highlight how the spec evolved, and we got that provisional spec out in November of 2021, and then we immediately implemented an SDK to get some live software working, so we could always be drawing experience from practical use cases. And then as we evolved, we worked on iterating on the provisional spec. We looked at GLTF's PBR materials to import those. We looked at all kinds of different issues that came up in practice, and along the way, we kept evolving the Anari SDK to work on those things. And that landed us finally in August of last year. We launched the 1.0 spec. Now, the 1.0 spec does not mean we have solved every problem in rendering for all domains, but what we've done is we've tried to settle on here are the things we think we won't need to change anymore, and has given us a nice solid foundation to then flesh out everything that the world of 3D rendering possibly could express. And so there's a lot of exciting things coming down the pipe, so we're really just getting started. And so since then, earlier this year, we started our adopters program, which is a way to officially claim conformance of being an implementer of the Anari API, and that helps us then fund and secure like our conformance test suite and the ecosystem that we all share. And then, of course, we've been continuing to work on the spec, and we've been continuing to work on the SDK. So in its entire story, it's been about 4 years worth of work, and it's only been 1 year since the 1.0 spec. But like I said, we're just getting started and things are getting very, very exciting. The one thing I'll highlight is that we're doing this all in public. So all of our spec development and the SDK is just all up on GitHub. And so we're wanting to get this in the hands of as many people as possible. So I want to talk a little bit about what it's like to design an API that looks like this. When you have an API that's high level and needs to talk to very diverse implementations, you have to balance what does API uniformity look like, so what are the things that look the same, and then what are ways that implementations can still express their secret sauce, so to speak. So on the API uniformity side, things like what do objects look like? They're based on handles. How do you parameterize them? How do you express array data in memory? How do you express the ownership of that? There's the actual scene hierarchy that you, as an application developer, share with an Anari backend, concurrency, parallelism, all of those things. These are the things that we believe that nobody really needs to do differently to, so this is what we want to standardize on. But then there's plenty of things that we expect implementations to make different choices. Just straight up, what features you decide are important to you. Anari, what we want to do is standardize how you spell those features, not who has to implement them. And so we leave that wide open. Our conformance is about, you claim conformance for what extensions you implement, not how many extensions you implement necessarily. Things like performance or certain hardware features that you want to expose, like ray tracing is a prime example. Of course, image quality is a great differentiator. If you have great global illumination, that's a great way to differentiate yourself. And then scene size is one that is actually quite diverse. I come from the HPC space, so I deal with volumes that are a terabyte in size on a regular basis, but that's a very diverse topic in and of itself. And so like really balancing these two things is a tricky thing to do. We think we've done a good job at it. And the way we approach this is Anari focuses on tell me what to render and when to render it, but Anari's letting the implementations figure out how that's done. And I think that will make more sense in looking at the software stack of how things get categorized when working with Anari. So this is the really high-level view of how that works. You have applications. They talk to the Anari API. That's really the implementation of Anari is the engine itself, and that's where you find, as an implementer, using things like lower-level graphics APIs. So I'm from NVIDIA, so what I'm going to do is walk from the bottom up for how me, as someone who also implements and provides an implementation of Anari, might view this. So I'm going to show you my first-person perspective, so go ahead and insert your own answers to these as we walk up the stack. So at its most basic level, it should shock nobody that someone from NVIDIA likes GPUs. But GPUs, CPUs, network hardware, there's lots of things that we can do to implement a renderer. And going one level up is where you find a lot of the really well-known graphics and compute APIs, so Optics, DirectX, Vulkan. This is where you're really implementing the how do you render the pixels, something that I do every day, but that's not what Anari is trying to get after. This is something Anari expects you to use to implement your engine. And so then the engines that get implemented themselves, those three that I've highlighted are ones that I primarily am involved with at NVIDIA, but this is where there's so many renderers out in the ecosystem, and all of them really are appropriate as Anari implementations. So if you're rendering 3D data, Anari is a great target for that. My primary one that I implement is VizRTX, and that's built on top of Optics and RTX GPUs. So then this is where Anari comes in. So basically for VizRTX, the one that I primarily maintain, the only API to get to it is Anari. There is no second API that I expose for anything else because I wrote it from the ground up to be that way. And that's hopefully leading the way of being an example as well as being a production renderer for certain sets of users. And I'll say on the top level, the reason I put scene graphs in its own little box is because the way you represent a 3D scene, often rendering isn't the only thing you're doing. And so with the scene that you represent with Anari is really only a scene representation for rendering. Scene graphs, the whole problem of how do I manage a scene that's going to do things like animation or physics or anything like that, Anari's not after those things. So the expectation is not Anari's trying to grow into this generic tool set. It's really only about interfacing to a 3D engine for the sake of making pixels, just to scope the problem. So that's the whole stack. There's a lot there. Love to talk more technical details if you have questions, but I wanted to kind of look at a more practical perspective of what does it look like to actually use the Anari API, because it is an API at the end of the day. It's not a file format, it's not doing anything, it's just a C API. So what an app does is compile against Anari.h. Anari.h has a bunch of C functions that link against the front-end library called libAnari. This is cross-platform. And so then those are compile time constraints, and then at runtime you can decide which Anari library you want to open and use, and then ultimately then it's uniform after that for all of those engines. And I will say, just one note, if you want to directly link a rendering engine and skip the dynamic loading step, that's totally possible, totally cool. But this is generally the most common way that applications get access to those engines. And then we took a page straight out of the playbook from Vulkan, and we can do layering. So the main thing you implement your application against is called an Anari device. And what we can do is say that an Anari device you talk to could actually be a device that's doing something that's maybe debugging, could be API tracing and stuff like that. And then you put a real device underneath that, and so then you can still get real pixels back. But this is the way we implement layering. The device abstraction works well. So before getting into any API details, I just wanted to say, hey, what's in the Anari SDK? And there's a lot. And so to kind of parse this image, I want to walk through it piece by piece for what's in there, because we decided to go with a mono repo approach for all of these tools. So at the end of the day, the thing that you're really here for is the front-end library. And this stack is roughly going to show what lives below and above the API, but when you look at the specification, you're looking for libAnari, this is the thing that you're after. And if you want to, you can, it's just a normal CMake project, so you can just go and turn everything off and only build this if that's what you're after. So where you're at in the stack then is that libAnari is what the dotted line is there. So that's what the front-end library is. There's a helper library inside of the SDK called Helium. I took a pun from the Mesa project, where there's this layer called Gallium that helps you implement a smaller thing that can then turn you into a larger like GL driver. Helium is the Anari version of that, and it's really small. It's a smaller element. It helps you get off the ground. Yeah, puns everywhere. And then it turns out more puns, because I used Helium to implement a sample device that combines Helium with Embry, just for the sake of showing how you could possibly implement the API. And a halide compound is any compound that is helium plus something else. So helium plus Embry turns into halide. Then there's some other devices that are more utility focused. So there's the debug layer. That's just a device implementation you can use. The sync device is an implementation that doesn't render anything, but it'll take all API calls. So what you can do is use it in a place if you're having issues with a particular device backend. It's a great way, it's just a practical tool if you want to take all of the possibilities out of your implementation dying. Like maybe you're using the debug layer with it, that can guarantee there's some robustness that you can make it through your application while you're debugging it. And then the remote device is a neat tool that you can take the Anari API and decide that you want to do rendering on a remote server, and you can forward all API calls there and then get images back. It's a neat tool in and of itself. Not a lot of time to talk about how it works, but just know that it exists, and I'm happy to talk about it with you if that's interesting. We have some things that sit just on top of the Anari API. We have some Python bindings, which has been already showing a lot of promise in a number of places. And then C++ wrappers, if you're like me and you like type safety from C++, great, you can use those. It's a header-only shim on top of the C API. And then if you like C, well, stick with that. That's totally cool. We have some samples that can show you how you might want to use the Anari API. The simple examples are really just single files to teach you one concept. So there's just a couple of them in there, and the whole point is not this is how you build an application. It's really trying to say here's an API concept that you can use. And then the viewer is really minimal, but it's just to give you something to start with, like load an OBJ file, load a GLTF file, and look at some things. It's really there just to give you a feel for something. It's not the product that we're trying to work on. There are some cool integrations we have with outside applications. So we have a Blender add-on that I would love to eventually upstream to Blender, but that's already got a number of useful things you can do. Like there was a press release from Kronos saying like, hey, Anari, we have stuff at SIGGRAPH, and then it was just a screenshot of the Blender add-on. And then HD Anari is a brand new thing we just put in the SDK where we're trying to expose Anari as a Hydra delegate inside of the OpenUSD ecosystem. This is just getting started, so it's very, very new and needs a lot of love, but we want to work on it in open source, so it's also in the SDK. Then the last thing that I'll mention is our conformance test suite lives in the SDK as well. It's not a separate repository, and that's based on our Python bindings. And then also the code gen tool stuff, I didn't know where to put it, but we have a whole JSON system for like generating our headers, even though it's not all that much. And then there's some just useful things for like metadata queries that we can generate for you just to make your life easier. Again, opt-in, you don't have to use them, but that also lives in the SDK. So again, a lot of stuff is there, but hopefully it's organized in a systematic enough way to not get lost when you're looking at it. Okay, so back to talking about the Anari front-end library. This is the thing that we're standardizing. And like I said, the main thing that you implement your application against is an Anari device. And so this is done with a C API, and we got C++ wrappers on top of it. But the device is really the instance of the implementation you're working with. So if you were to say, what's my instance of VizRTX? That's the VizRTX device. So this is not the library. This is the live thing you're talking to with the API. And so 2 lines of code to load one of these things. VizRTX you would load with an Anari load library. You get a handle to a library object, and then you can create a device from that. The default is always guaranteed to exist. And so like that, 2 lines of code, you already have an Anari device ready to go. A core concept in the Anari API is that objects are represented by opaque handles. And the whole point is we're not trying to standardize implementation details. And so there's just some really basic concepts I'll walk through that will actually get you through understanding most of the API. They're reference counted. It's pretty straightforward. And then they're configured with parameters. So for us, the name parameter means information that goes into an object. And then properties is information that comes out. Those are not the same concept. The idea is parameters are things that the implementation can't possibly know that needs to come from the app, which is most things. And properties is information coming out of the device that the app can't possibly know. And so that's like the base of those 2 concepts. And the central part of parameters is that they're transactional. So the way it works is you do a bunch of parameter setting, and then you say object commit. You commit the object. And then what that expresses is everything that I've set is now going to be visible in the next frame. And the reason that's so ambiguous is because there's a million ways you might want to do that. But semantically, and in terms of like concurrency and parallelism thread safety, those guarantees are easy. And then the mechanics of what that actually means is left up to your implementation. And I also wanted to note that parameters are primarily unidirectional. And so what I mean by that is the idea is you set a parameter and you just had the value that you set. And so where that value came from could be some scene graph somewhere in your app, how you want to organize those things. Anari is not a central data store to be doing all kinds of things with. So the implementation may put that value straight on a GPU. It may send it over a network. The idea is that you don't use Anari as your central data representation to do all this stuff. Just hold on to values if you want to use them for some other purpose, like putting them in a user interface. So just be aware that that's an intentional concept. So just to look at a brief amount of code, creating objects is pretty straightforward. There's a set of object types that you work with. Some of them need a subtype, some of them don't. So worlds don't, there's just worlds are a thing. And then if you need a subtype, there's a queryable set of values that your implementation gives you. But there's some standard ones, that's the things we standardize in the spec. So like a perspective camera, really straightforward. So looking at setting parameters, hopefully this is easy to reason about. You have the device implementation you're talking to, the object, like a camera here that you're wanting to parameterize, the name of the parameter you're setting, and then the type and a pointer to that type that it will mem copy from after that call is over. So that's how you set some camera parameters. And then of course, to actually have those show up in the next frame, you commit your object and then move on to other things. The object hierarchy that you express with Anari is frame-centric, and all of these objects can be in more than one parent. So the idea is I could have a single frame with a camera, world, and renderer, and maybe I have another frame that has the same world but a different camera. So you have two different camera positions. But you can mix and match these things how you want. The idea is where it says one-to-one is where it's just like one parameter or one object handle is set as a parameter on another, and then 1 to n is there's an array of these handles you express to get like all of the instances in the world, for example. So then the last concept I want to show you is rendering frames. This is really what you come for with Anari. You want to make pixels. And so Anari render frames in asynchronous operations. So you'll see like we kick off a frame and then immediately decide to synchronize with it. The idea is if you have a really long running frame, you don't want to block your UI, or maybe you want to have a bunch of frames in flight at the same time. That's hopefully really straightforward. And then mapping out pixels, pretty straightforward. There are buffers of various channels of information. Here we get the color channel out, just get a pointer to those pixels, and we can then output them to a PNG. You could put them up in a user interface somewhere interactively, but it is that little amount of code. And then you just unmap your frame. And really, with what I've just shown you in the API, you have the basics for making cool images like this. Because what you're saying is, like, for instance, for this, here are the streamlines, here are the material parameters, here's the building meshes, here's the camera position, and then you get the frame out. The rendering engine itself is what's making that look beautiful, or making that scalable, making that fast. Anari's really just hooking those two things together. And so there's a ton of topics that I'm not going to go into here, but I would love to talk about them with you if you would like. There's just a bunch of object subtypes to talk about and what each of those look like. Device introspection is an interesting topic. You can ask your device implementation, hey, what are the object subtypes that you have? Those subtypes, what are the parameters and their limits and such? That's information you can get at runtime. All the asynchronous stuff, like rendering versus scene updates and thread safety guarantees, we've thought about all of those, specified those things. It's not that complicated. I mean, I'm not trying to say multi-threading is not complicated. It certainly is. At least Anari's role in those definitions, I think, are somewhat straightforward to reason about. There's multi-frame and multi-device. So you can use multiple devices at the same time. So if I wanted to have two different rendering views running in parallel, you certainly can do that. There's multi-frame stuff and the performance considerations of that. Those are all interesting topics. Array ownership and semantics, another thing. There's GPU interop is another piece of that story. And then there's a ton of different ways you can implement a 3D renderer, and they're all valid in the Anari ecosystem. And so really talking about what's the best way to do X, Y, or Z is a good discussion, but just kind of outside the scope of learning about what the Anari API is doing. And so with balancing these things, there's kind of two things I just want to really hammer home with some examples, and that's this API uniformity versus feature differentiation. And so the API uniformity is what makes Anari portable. So the things that look the same means every single time we put Anari in an application, the story is largely the same. You do an integration once, and then suddenly all of these renderers just work. And that's been a really satisfying story, everything from our Blender add-on, we've done some really cool things in Omniverse. That's a whole talk in and of itself. ParaView is a really common open source scientific visualization pipeline tool that works really well. Visit's another one. VMD is a really cool large-scale molecular dynamics visualization app that I've worked closely with the developer on. And then the one thing I wanted to highlight in this bottom right is a little tool I wrote to develop VisRTX. And so I love DRM GUI. It's a lovely framework for making little UI apps. The thing I find really, really helpful with Anari is it's very ergonomic for even doing small scale app development. So yes, it's fun to motivate like being able to get a renderer into big tools, but we never want to leave behind people needing to just write little tools for themselves for whatever you're doing. And I do that all the time, every day. And so I just want to say that's not lost, and that's actually an intentional part of the simplicity of the Anari API. But then on top of that, Anari's being scalable is a key part of what we want to be able to express through the API. So the scalability, really the dimensions of that is up to what you find important. That could just be just how great your image quality is, the amount of hardware that your rendering engine can use at any one time, your frame rates, of course, really obvious scalability one, scene size, and then animation update rates. These are all things that a rendering engine can decide to make the primary thing that's most important. And Anari is sufficiently high level enough that you can get the goods out of a rendering engine that's really great at animation. You can get another one that's really great at just great global illumination. And there's no reason to reach for different APIs to drive both of those. So one thing I wanted to highlight was some interesting research that I've been primarily working on, just to give you kind of a narrative of what it's like to use Anari to solve bigger problems, because we're really trying to get out of the way of people solving problems. So a colleague of mine, Ingo Wald, he's been publishing on ray tracing for decades now, and he wrote a couple of papers on how do you do distributed memory path tracing. Really fun problem to work on. Published a couple of papers at HPG on that, but really this question came up of, well, if I were to implement my renderer on GitHub, how am I going to get it into various applications? And so he wrote a renderer called Barney. It's up on GitHub, and I convinced him he should put it under the Anari API so we could get access to some of these mainstream visualization applications that I work with a lot. And so if we remember this stack, this is the general layout of where things live. For Barney, it looked like this. We had VTK and Pair Review, Visit, Ascent, and others that we wanted to run in a distributed context. Those were the apps we were targeting. Those were already integrated with the Anari API. And so then we made Barney a device backend to the Anari API. He built Barney on top of CUDA, optics, and MPI, using GPUs and high-performance HPC network hardware. And really, this is the stack for that context, and we were able to do some really, really cool work that just was trivial to get running. Because the renderer was just working, by putting it under the Anari API, we were able to run some really cool, hundreds of GPU runs to DNS volume. I think that was actually 128 GPUs across I forget how many nodes. Ascent is an in situ rendering framework that is used for in situ. Just means if you run a distributed scientific code, if you just have those nodes already doing the simulation, you can use those same nodes to then do visualization, to do rendering, and that's what we did there with those. But all of these data sets are huge. They need multiple nodes to be able to render the entire data. So these scenes are spread out across multiple nodes in a cluster, but we could make single images of them. And Barney was the key to being able to make any of these pictures at all, and they're all interactive, by the way. At being able to explore these in real time is really exciting. And so we decided to write a paper just telling this narrative. So if you want to go read the details of how we went from a really cool research renderer to getting it into production visualization systems, you can Google that. We have a preprint up on Arvix. It's freely available, so if you Google that, you'll be able to find it pretty easily. So what I want to leave you with is some calls to action. And there's different levels of what I would like to call you into our ecosystem with. First thing first is just try out the Anari SDK. Go write your first Hello World program with Anari. I would hope that's a straightforward process. It doesn't matter if this is your first time looking at anything in 3D graphics or you've been doing this for years. I'd love to hear your feedback about how easy it was to get going with Anari, because of course it's trivial for me to say it's easy, but I'd like to know if that's actually true with you too. I would like to invite you to consider implementing an Anari interface in your existing app. So if you have a 3D app that you work on, you don't have to replace your whole graphics system straight up. Try to figure out how to talk to Anari first, and then see if it's been a good API to map to the way you express your scenes. And then we've got a bunch of implementations that are all free. They're all up on GitHub. They're all open source. Get your hands on some of those and see what the different trade-offs and implementation goods that those bring. Just go get some experience with it. One thing I wanted to also highlight is there's a lot of people, especially at places like SIGGRAPH, that work on renderers themselves, using Vulkan, GL, other things like optics. I'd love for you to consider what does it look like to implement your renderer as an Anari backend. There's, like I said, in the Anari SDK, there's a lot of tools to help you make that as low overhead as possible, in both in your time, and then of course you're also your code overhead as well. So I'd love you to consider implementing an Anari backend with your engine. And then there's also getting involved with the standard itself. So there's a lot of ways to do this. The first is if your organization is already a part of Kronos, come join our working group. We'd love to have you. We meet on Wednesdays at 10 a.m. Pacific. We try to keep that meeting useful and efficient such that we don't want to just spend time together just to spend time together. We want to get a lot of work done, and we've been good at that over the last couple of years. And then there's also the Anari advisory panel. So if you are unable to be a Kronos member, we still want to hear from you and have design discussions about the API. Talk to me if you'd like to join that. I would love to have you there. And then of course, like even if those top two things aren't interesting, participate on GitHub. We have GitHub issues both on the spec and the SDK. We'd love to hear from you at any level. Just want to get as much feedback as we possibly can. So I'm going to leave this slide up. Maybe this is a great way to kick off what our possible discussion could be. Because so I've talked for a half an hour, but we have another half an hour potentially to have interesting discussion. I'd love to hear from you, experience what is interesting, what's not interesting with Anari, just to get things going. So thanks, appreciate it. All right, do we have any questions?
Yeah, so I write on renders, so you can kind of mention that's who you're targeting, kind of. But I was really curious about how you did the asynchronous or the multi-threaded framing, because I'm running into bottlenecks with my own engine, so that's something that would be very useful for me.
Yeah, so we have to remember where Anari is in the stack. So a very valid implementation detail is you're going to spin up threads in your engine to manage things like multiple Vulkan queues or something like that, where what you're getting from Anari is fairly high level. Like, here's all the meshes. Now, you might do a parallel Thor over like building BVHs in, like, I'm a ray tracing guy, so if you're building BVHs over all of your bottom level acceleration structures, you can do that in parallel. Anari is not asking the application to manage all of that. So that's part of your responsibility as an engine implementer. And then really when it comes to thread safety with Anari, it's really what can I do, what functions can I be inside of in parallel with multiple threads. And sometimes that is, of course, useful for performance in the application. Like if you have lots of Anari objects that you're manipulating with like animations and stuff like that. The thread safety guarantees that are opt-in, so there's an extension that says you're allowed to do this, and a lot of implementations do. The idea is we currently say that thread parallelism is valid between objects from the same device that are different objects themselves. So I can like set parameters and commit one object while I'm set parameters and committing on another. Some devices that might actually be a problem. Usually it's GL is the culprit. But I'll say straight up, you can always have thread safety between devices. So if you had two viewports with two different things, those can be done in parallel. So yeah, there's a lot of nuance in there, but hopefully that's making some sense.
Right.
Yeah.
I'm thinking even like a thread for reading, a thread for writing, something like that.
Yeah.
So like, I'm generating images, textures, and that kind of slows things down sometimes,
Yeah, certainly. And so if you have worker threads working on those things, by the time you get to Anari, it's, okay, the texture generation's done. Right. I'm going to make an Anari array, put that on an image sampler, and I'm going to put that on one of my materials. That can all be done in parallel to a frame that's running. That's actually a concurrency problem, not necessarily thread parallel. You don't need threads to do frame concurrency there. But yeah, that's all stuff we expect people to do.
Hi, thanks for the talk.
Yeah.
I was wondering if you thought about rollback or cancellation.
Yeah, so we have exactly one function for this called Anari discard frame. So, I think it's just Anari discard. Anyway, yes, but it's only at the frame level. And so I don't think we have any other ops you can cancel, but I'm not sure how you would. But yeah, the one thing you can kick off asynchronously can be canceled. But it is your implementation choice all you can signal is I want to do a cancel. You can't actually like guarantee that your implementation decided to not decide to block until that frame was over. And so if you find that to be the case, you should complain to your vendor, like, please implement cancellation, Yeah.
All right.
Yep.
I have one more question. So we have render. So I implement both DCC and rendering.
Mm-hmm.
So we have renderer differentiation.
Mm-hmm.
Now, doesn't that mean if we want to we want to have our renderer in, I don't know, Blender or something,
Mm-hmm.
You need to do some extra work on the Blender side of things if
Yeah.
you talk to Anari.
Yeah, let me find the place that is. Actually, this might be a larger picture. So there's a couple things. One is with Anari, there's some objects that like Blender just has to know. Like Blender just has to know how to set a triangle mesh. So the story for that specifically is there's the renderer object, which encodes what are the settings for the specific renderer I'm using inside a device, so a device can have more than one renderer. And so like in our add-on, we dynamically generate the UI for all of the renderers in a particular device. So this one was VizRTX, and like all of those things, except for like maybe 2 or 3 of them, are unique VizRTX renderer settings. And so that is being pulled from the Anari device. So if you loaded up Helide or Osprey or something, that UI would change based on that. But like Blender's just going to say, here are the lights I know how to set, here are the materials I know how to set, et cetera. So that's an interesting discussion to talk about what that might look like. Good.
So for automatically generating that UI, are you able to query metadata on the parameters that the that different backends support?
Yeah, so you can get min, max, defaults, and I think there's like a usage hint, like is this a color or not? I think that's all we've started with, but we've crafted it such that we can extend that with arbitrary amounts of other things that people find useful. That's just, we've gotten a lot done with just those things so far.
Okay, and those are, because you had the 2 types. You had the forward data and the backward data. I forget, one was properties, the other was
Yeah, parameters and properties. Yeah.
parameters and properties. So is that the case for both of those?
So actually don't know if we have metadata query for properties. I mean, probably. I only use them for parameters, but we certainly should. There's no reason we shouldn't for properties as well. You would have to know like what your property is that you're wanting to ask for. And so there, I'll just say, put a little meat under, there's this tension of like, am I allowed, or am I able to write an application that knows nothing about any object in Anari versus like, what are the things that I want to defer to runtime to learn about? Really, the renderer is the thing you find most often, yeah.
Yeah, so what about objects that aren't under a specific, like more general, like of the scene graph? Like, can you query defaults for that? And what about more complex objects within the scene graph?
Yeah.
Like, so this seems very similar to the Intel Osprey API. And in that case, you might have more complex objects that need to be configured a certain way.
Yeah.
And sometimes documentation doesn't fully explain that, and the interface is completely opaque, so you kind of can't get that information back.
Yeah, so the way we handle this is you can ask for, okay, let me start with all object subtypes are extensions. And so what you do is you say, my application like needs to know what a triangle mesh is, what like the PBR material is, et cetera. And usually the way it works is you get to make a choice when you initialize a device. You can say, do you implement the extensions I care about? And that then is a fork in the road of, is that a fatal thing? So like, for instance, if I can't display triangles for some reason, maybe I have a volume-only renderer, do I even want to let my user try? But there's also the path of, we say that by default, all object subtypes that a device doesn't understand is allowed to just ignore, and should ignore, so it should not be fatal. So you can still run it. You just might have things missing in your frame because your device doesn't implement it. And so we give you the hook to say, I want to refuse even trying. And we also accommodate people that say like, just let me try anyway and see what happens. So then there's the question about querying that. So all of that information is in our object queries. Materials is probably one that also has a lot of UI associated with it. I don't know if you would want to put a lot of UI on like, I'm like setting my triangle vertex buffer array or something like that, but it is in there.
So there are additional things, like, for example, with querying support, so with like more complicated things like unstructured grids.
Yep.
So I know that in some cases, some APIs might support, say, they might support unstructured grids, but then they might have different, like, for example, Osprey has different backends for
Right.
that, and the different backends support different things
Yes.
within unstructured grids.
Yes.
So how do you handle all that additional complexity in there, and making sure that we can ensure like a consistent experience for the end user there?
So the way that would work is the device is the one that reports what extensions it implements. And so at the end of the day, you would probably just write the code for working with like Osprey's unstructured volumes. And so you have that code, and then you get to decide whether like you load up a particular Osprey device that does or doesn't support those unstructured volumes. You could report that as a warning to your user. You could just say like, you don't even make that an option to load in your app. You would write the code for that extension straight up, and then your decision to enable that code for a backend that doesn't implement it or not is then up to you, if that makes sense.
For the scalability case, can you give a good example of how the Anari might be used to maximize the value of your GPU, multi-GPU cases, for example?
Yeah. So that is technically a rendering engine specific answer. So like for instance, VizRTX I just made it so simple because it's just like a part-time thing for me. It'll just use whatever GPU you initialize it with. But like Index or Barney are built to look for as many as possible that are available. So if you have a multi-GPU workstation you're working on, you can, by default, Barney will be like, I'm going to use all of them at once. So the application here, like you'll have some device parameters so the device itself is an object that you can like set parameters on. So you can ask your device like, what are the things I can set? So Barney might be like, please use only these GPU IDs or not. But it's Barney that would be the one saying, I'm giving you those hooks to be able to control which GPUs you run on. The Anari API itself makes no assumption about what hardware you're using or anything like that. So it's weird because Anari is then this vehicle for you to talk to an implementation, but that implementation is still responsible for giving you those options, if that makes sense.
Does it when you do this, what is the benefit of the NVIDIA implementing Anari for usage of the GPUs or parallel processing nature?
Yeah, so the idea is when you say Anari render frame, like that's VizRTX. If you were to run Helide, it's like 50 times slower. So like the value is I can make it really fast because our GPUs are really fast. But that's the thing I decided to say, like that's the value VizRTX gives you. There are other GPU accelerated renders that are still going to be faster than Helide, but are slower than VizRTX because like that's not a super compelling shading example with that car in the lower right. So VizRTX is being simple just to be fast, but that's my choice as an implementer. Sorry, there's someone with a mic back here.
I'll just go right in then. Earlier you said that objects are wrapped in opaque handles and that they are reference counted.
Yes.
So I'm assuming when you're specifying a mesh or any kind of object that is a superset of other objects, they take those object handles as parameters when you're passing them in. So
Yeah.
a mesh might reference a texture. Does that mean when everything that references, say, this texture is deallocated or is destructed on the Anari implementer side, Anari implicitly calls the destructor or like a destruct function that the Anari backend is bound to?
Yeah, the way we handle that is the semantic is you get a handle back from the API when you say like Anari new array. That handle has one application reference count. Now I'm going to set parameter that array handle on, let's say, my triangle mesh or texture, whatever it is. And internally, there has to be enough reference counting that if I decide to release the handle from the application, that the internal guts have to live long enough for those other handles that I still have from the application are still valid. I can explain to you the mechanics of how we do the different ownership models for arrays specifically, but the idea is you're, from an application perspective, just releasing your references to it, and then you don't participate in the internal guts of like how, of like when an internal object would go away. There's some really straightforward strategies to make that nice and robust and easy. But at the end of the day, the reference counting has a very specific application usage semantic And then there's even some options for how you would want to handle that internally. So for example, in VizRTX, as soon as you've released an object, all of the host side stuff I might just throw out, knowing that it's already on the device. I'll just leave it there, knowing it can never change because the application basically revoked its ability to set new parameters on it. So, but I can do that internally if I want to.
Okay. Is there maybe plans to maybe provide an extension to allow the Anari implementer to overload this reference counting functionality if they think maybe they could do it a little better or more targeted for their application?
Yeah, that's. I would love to hear what ideas you have, because the semantic is so thin. It's because what you're saying when you say Anari retain and release is you're saying I'm like when you get a handle back when you first create it, the application's ref counts 1, and then anything internal is just never the application's business, because what we fear or what we want to keep away from is you design this app that needs specific reference counting semantics that only one device implements. That just kills the portability story with Anari. But if there's something we've missed, I'd love to hear about it. I'd love to hear ideas.
So if you have to deal with all the complexity of the render, then porting to any given renderer is actually not that hard. I mean, you could just make all the appropriate calls, and it's really about all the complexity of all the calls you have to make, that really why you have to call, not just that you have to call. So is there any concept of where you can abstract away, where the visualization application doesn't need to understand all of the aspects of what makes this picture pretty, like being able to have pre-made stages and just say, use this stage, so all this complex lighting for this particular environment is, the application is not dealing with that.
Right.
Or the complexity of the low-level details of the BRDFs of the material, it's not dealing with that. It's just saying chrome. It's, you know, or it's because you can't make a more beautiful picture with the same parameters that you're handing OpenGL,
right.
You know, a basic render.
Right.
And if the way you make beautiful images is by the complexity of how you describe what you want to do.
Yeah.
So how do you do that without having it become the responsibility of the visualization application?
Yeah, so for instance, VizRTX is a great example of this. VizRTX implements the Chronos PBR material that's a part of the Anari spec. Not the only material that could be PBR, for what it's worth. It's just what we started with. But just for the sake of simplicity, I only implement like roughness and metallic. And that for my customers, and opacity and base color. But for my customers, that's like good enough. And so like if someone like sets all kinds of parameters on the PBR material, it might only show up in Osprey or Cycles or something because they actually implement the full PBR material spec. And the application still works with VizRTX, and it looks simpler, and it's not completely, you know, foreign. But the expectation would be is an application sets the best parameters it can for like the most advanced implementation for whatever it cares about. And then the implementation still is free to simplify that. What you can't go is the other direction. I can't take like the matte material, or very simple diffuse only material, and then suddenly turn it into like a beautiful like clear coat gloss look, because you would need a better material spec for that.
You could imagine a configuration file though, where you could provide extra parameters that would get used, and I guess that would just that's
what it is basically if you have all of those, use the PBR material, and then if you load a backend that just has a simplified material model, it might give you a less than perfect image, and that's the approach we took. Yeah.
Yeah. So thanks for the talk. Great talk. So one question I have about the frame rendering. So if I'm an app developer and I'm working on bridging through Anari, and I wanted to create, for example, a spiral tiling renderer or some sort of accumulating renderer.
Yeah.
Am I working on a single frame at a time?
Yes.
And I'm subdividing and like sending little frames as my render?
So if you wanted to go spiral, there's two options. You could do that where you decide to implement the spiral yourself, and that would technically work. But then if there's an implementation out there, like VizRTX will give you like a checkerboarding option, where I can do progressive refinement from a very coarse resolution and then refine it myself, but I'm the one doing that internal. So if you do a spiral renderer yourself, you're just going to make everybody do the same thing, essentially. You could make that like one mode, like you could just say there's full frame mode, a spiral mode, or something like that. But we expect rendering engines to, like, if you're an offline renderer, to give you maybe it's a render parameter option to say like, here's my spiraling option or something, so you could control that. Like we would expect an engine implementer to give you that option, but we just haven't standardized that yet because we have like offline renderers and we have like super real-time renderers, and just we haven't had that as a standardization point, but could be interesting in the future.
Yeah, because I can see, I mean, that's a common thing for every renderer is like, are they, traditional, like scanline renders, and then you had full frame renders, and you had, progressive scatter renders, and spiral renders, tile renders. Yeah. Okay.
Cool.
Thanks.
Yeah.
So kind of, I guess, piggybacking off of that, so that's kind of a feature that would be similar for different backends, but also potentially very different. So for example, like kind of like a multi-resolution progressive refinement approach would make perfect sense for, say, a ray tracing based renderer, but maybe not so much for like a rasterization based renderer. But you're saying that in those cases, those options would be like specific extensions for that backend.
Yeah.
So how do you handle, is that like just that one specific thing, or is that, 'cause there's lots of other things that might follow a similar pattern where, there's kind of this unified idea of I want to do progressive rendering, or I want to do like dynamic, resolution scaling or something like that. But there isn't like one universal thing that applies to different renderers. So another thing I'm thinking of is like unstructured like data formats, like those things. Like different rendering backends might expect that data in different formats. Do we have to conform to each rendering backend and like their extension of that, or is there like a unified a unified API that kind of like takes your input and then translates it to the other data?
Yeah, so I'll
backends.
first approach this from this perspective, and then we can talk about maybe what that would look like for multi-resolution, like spatial fields, essentially. But really what it boils down to is we have an extension in the Anari SDK for progressive rendering. So basically, is Anari render frame a single shot operation, or is it going to be something that's expected to be basically spun on in an arbitrary length of time? And that's really what the application interaction with is. So if it's a single shot renderer, basically you would render and then just expect that you're displayed on screen, then you're done until there's reason to render again. And like with ray tracers, the idea is you just are always spinning on an Anari render frame, and then when a frame's done, you map it out, you display it, and you just keep doing that and doing that and doing that. And the implementation is responsible for deciding when accumulation resets, so that's not something the app even worries about. So really at this level of abstraction, the only thing you're actually specializing on is, am I going to do that once? Like VTK does that, has like a single shot architecture, or are you just going to keep an Anari render frame, display, an Anari render frame, display, expecting it to refine? That's really what they all end up boiling down to. On the multi-resolution front, I have some ideas for what that could look like. Right now, we just expect your implementation might give you different like LODs essentially. Like that's not an explicit concept in the Anari API. It certainly could be. We just need implementations that want to do that because we want to be driven by practice. So we're open to it.
So I have one more follow-up question on you touched on this before on the concept of threading and maybe also the cancellation aspect. So this API, I think it seems like it would allow for a pretty simple just thread separation. So does all the logic all the logic that's happening in Anari and then all the logic that happens within the backend renderer, does that happen on the same thread that you're using, that you're calling the data from, or does it move that to a separate thread? And does that differ, say, if you were to do different kinds of data ownership settings? So like if you were to say you own this data, does it just say, okay, you have this data, you can work on it in a different thread, or is there consideration for that sort of stuff?
Yeah,
and then just
certainly.
sorry, go ahead.
Yeah, certainly. So what we speak about in the spec is what is the application's relationship to the implementation threading-wise. We don't prescribe how an internal threading model might work. So we actually have diversity of this. So VizGL, for example, a GL implementation, to kind of deal with the thread safety issues of GL, there's just this background thread that just takes all API calls as commands. And so but that's VizGL's choice versus VizRTX is just stuffing things on an Anari or on a CUDA stream. And we get asynchrony just by natural use of CUDA streams to decouple GPU work and CPU work. And that ends up being implementation choice. If we wanted, we'd be totally open to having a layer that could turn any backend into one of these background thread VizGL style things. We could do that, but apps don't worry about that.
Oh, just a sec. We
Yeah.
got to get this on the audio for. Yeah, and we only have two.
And we have another question back here too. Yeah.
Oh, sorry. I guess I was more referring regardless of what the backend is doing. I'm more so about wondering if the Anari layer itself offloads the.
So it does nothing. Really, the front end library is just saying I have Anari commit parameters, and I'm going to invoke your internal Anari commit parameters.
Okay.
And it's up for you to decide to do something. It does very little right now, but we could of course do interesting things later. It's just code. We can change it.
We've got one last question here.
Thank you for the presentation. I was wondering if you see Anari as a feasible API to build game engines real time, and if it could target mobile devices or lower end and web.
Yeah. So 3 things there: the size of hardware you're trying to target, the domain being games, and then also what's the web story. So I'm going to address all 3 of those separately. First is there is no target environment that is so that it's basically if you have an implementation that runs on something like a microcontroller, Anari is just a C API. It's really getting out of your way. It doesn't assume you're on an HPC system. So hopefully that's helpful. On the games question, I want to say yes, but I'll talk about AAA games because those are generally the most demanding. What ends up happening is the rendering engine is very much built for specific content. And with if you're a console developer, you're really wanting to control the implementation choices of every single thing on that console, on that machine. And so you certainly could put Anari in there, but at the biggest games that are most complex, generally they're not looking for portability. So it's kind of you write an engine for maybe a couple of games, and then you rewrite that for another couple of games. And so it's not that Anari is not appropriate, it just might not be it's probably the least important application domain we're trying to get after, and they might be least interested in it. That said, it'd be amazing to build a game on top of Anari and have different backends that you use for your graphics API. If you end up doing stuff like that, basically the GPU interop story, can you compose compute shaders and your rendering ops through an Anari backend? Can you make those talk to each other with low overhead? Absolutely, we want to make that happen. We just haven't got there yet because those people haven't been in the room, but we would love to see that happen.